And now I'd like to welcome Allison McDonald, the co-coordinator of the PAUSE panel webinar series, to introduce our speaker today. Allison?
Hello. Thank you, Mike. So today it's my pleasure to introduce Mariana Biff. I met Mariana at AGU this past December, where I saw her presentation, and I immediately thought it would make a wonderful addition to our webinar series, as it speaks directly to our PAUSE panel priority that's focused on West Coast ecosystem variability and prediction. Mariana received her bachelor's and master's degrees in physical, chemical, and geological oceanography from the Federal University of Rio Grande in Brazil. And there she studied the effects of harmful algae blooms in both freshwater systems and in the South Atlantic Ocean. While continuing this research, which she now does in the South Florida marine system, she's working on her PhD at the University of Miami Erasmus through a scholarship from Brazil's National Council for Scientific and Technological Development. At Erasmus, her advisor is Dennis Hansel, and her thesis focuses on improving our understanding of the controls of organic carbon accumulation in the upper ocean, using incubations and observations to explain biogeochemical dynamics. She has a particular interest in the applicability of biogeochemical float data to this subject. Along with this research, she's also using isotope techniques to look for sources and sinks of dissolved organic carbon and nitrogen in the South Pacific and the Arctic Oceans. This last she's doing in collaboration with groups at University of Massachusetts, University of South Carolina, and University of Connecticut. And if all of this doesn't sound like enough for a PhD student, she's racking up an impressive amount of time at sea in the Atlantic, Pacific, and Southern Oceans. And in 2017, she won the Erasmus Marine Roach Award for outstanding research at sea. Today, she is here to speak to us about the impact of Northeast Pacific warm events on organic carbon production. So welcome, Mariana. The screen is yours.
Thank you, Alison. Thank you so much for inviting me to talk here. Good afternoon, everyone. Thank you for being here in this webinar. So, yeah, as Alison said, I'm talking about the impact of warm events on organic carbon production in the Northeast Pacific Ocean. So first of all, I'm going to give you a brief background on organic carbon production, how it's produced, consumed, and a little bit of the global distribution. And then I'm going to enter into how organic carbon production was influenced by the warm events in the Northeast Pacific Ocean between 2013 and 2016. So organic carbon is produced in the upper ocean, in the euphotic layer, by primary producers, so mainly by phytoplankton. And basically, phytoplankton picks up inorganic carbon and inorganic nutrients and build up their biomass, which is called particulate organic carbon. And by actively release through excretion or through grazing, they release dissolved organic carbon as well in the upper ocean. And in the other end member, we have the heterotrophs, the bacteria that eat up this organic carbon and transform this carbon back to the atmosphere as CO2 and consume oxygen. But these reactions are not 100% efficient, and a little bit of organic carbon accumulates in the upper ocean in the form of POC and DOC, a particulate organic carbon and dissolved organic carbon. So the carbon that does not go back to the CO2 in the upper ocean throughout all of these biochemical processes is called net community production, and it's a very well-known concept already. So after POC and DOC are produced, they can be exported to the deep ocean. So POC mainly through sinking particles and DOC through overturning circulation or during a winter mixing that brings high concentrations that accumulate at the surface to the deeper water masses. So if we take a look at the global distribution of dissolved organic carbon, we see that the background of the ocean is never zero. And this is because some of this DOC is resistant to bacterial remineralization. But as the water mass ages, this DOC is gradually consumed by bacteria, by heterotrophs. And as we can see, for example, here in the Pacific, the older water masses carry lower concentrations of DOC, but it's still a lot of DOC. If we sum all of the bulk of this organic carbon in the ocean, we get into 662 petagrams of carbon, which is equivalent of CO2 in the atmosphere. And this is the reason why it's interesting to understand their dynamics. There are a lot of different ways to measure this net community production or this organic carbon production in excess. And I'm giving you an example of a seasonal environment where we have production of organic carbon in excess. So as an example of the Northeast Pacific Ocean during the winter, we have the winter mixing. We don't have a lot of sunlight, so the phytoplankton is not really building a biomass in excess, in organic carbon production in excess. But there is an increase in the availability of inorganic nutrients that come from below. Towards the spring and summer, we have an increase in acidification, and the phytoplankton cells remain at the euphoric layer, and with this abundance of inorganic nutrients, such as nitrates, which is very important in the structure of the cells, they pick up then inorganic carbon and inorganic nutrients and transform into excess of organic carbon. So if we know how much inorganic nutrients this microbial community picks up during a certain amount of time, and we convert into carbon units through mass balance, we can then estimate indirectly net community production. So for example, in an oceanic region that is not really influenced by nitrogen fixation, denitrification, and for example, terrestrial inputs. Nitrate is the main inorganic nutrient that the community takes up, and we can use the Redfield ratio to convert this nitrate into moles of carbon and then estimate net community production. So if we have a regular measurement of nitrate in a region, we can estimate net community production. So as we saw, organic carbon production depends on nutrients brought by, in seasonal environments brought by this winter mixing. But during 2013 and 2016, a series of warm events impacted the Northeast Pacific Ocean for consecutive winters. And we were wondering what was the impact of warm events in this organic carbon production, because if a warming ocean increases acidification during the winter, is there an impact in the amount of organic carbon that was produced during the years of those warm events? So since the Northeast Pacific Ocean is a highly seasonal environment, it's a very suitable place to understand the impact. So the objective of this work was to evaluate the impact of ocean atmospheric oscillations, such as El Niño Southern Oscillation and the blob event, on the magnitude of organic carbon production. So these warm events started in the fall to the winter of 2013 to 2014 with a blob event, which was very known to cause big consequences to the west coast of the United States, and the fisheries and crabs collapsed. And in 2014, there was a very warm propagation of waters in the west coast of the United States. And then 2015, we had a very strong El Niño. So all of these warm events impacted the region at different years and sometimes together. And we were trying to understand the impact in organic carbon production. So first, we wanted to understand what was going on between those years. So we used ocean atmospheric, we evaluated these ocean atmospheric oscillations between 1950 and 2018 using sea surface temperature and sea level pressure anomalies from data from NOAA and NCAR reanalysis, just to understand who were the responsibles for each year of the warm event. Then, fortunately, in the same region, VGC floats were deployed between 2009 and 2018 in the Gulf of Alaska, in the Northeast Pacific, and they were they contain nitrate sensors. So we had very high resolution measurements of nitrate in the region, and we used this data then to calculate the high resolution net community production in the region before, during, and after this warm event. So what was the organic carbon production during those years? So going to the results, what happened with the ocean atmospheric oscillations between 2013 and 2016. So we understood that between 2013 and 2014, during that winter, there was an atmospheric ridge forcing the warm event, the blob pattern So what happened is that the wind in the region slowed down, and this reduced the sea surface cooling in the region. So in the North Pacific Ocean, it's not that the blob was actively warming the ocean, but that winter there was a lack of cooling of the upper ocean. So this had a feedback on the El Nino that was forming in the equatorial Pacific Ocean. And this feedback created in the winter of 2015 a warm wave of water in the upper ocean in the west coast of the United States. So it was a teleconnection between the El Nino and the blob. So basically the blob fed and amplified the El Nino that was being formed in 2014. And this El Nino consequently fed the blob that was already existing in the Northeast Pacific Ocean. So in the winter of 2016, then, as we can see here, this square is our region, is our study region. It was not very warm anymore, but the El Nino was fully developed in the equatorial Pacific. So for the winter of 2014 and the winter of 2015, we had very high warm waters in here, but in 2016, not so much anymore. And what was the response in the ocean? So these are the ocean observations. These are the BGC float data and a little bit of our calculations of organic carbon production. So let's take a look at these first three graphs over here. Before the warm events happened. So between 2009 and 2013, we have a very strong seasonality in the Northeast Pacific Ocean. So temperature, nitrate, our inorganic nutrient, and organic carbon production calculated from the nitrate drawdown. So as you can see in the winter, we have very low temperatures, and towards spring and summer, we have consumption of inorganic nutrients, and we have production of organic carbon in excess for the upper 60, 75 meters of depth. So during the blob, what we can see in here in this temperature, we already see that there is an increase in the stratification. So this stratification from the summer was not entirely broken down. We don't really see in the, it's not sensitive enough for our colors here to see, but our nitrate was not as available as in the previous years through winter mixing. But we have very increased organic carbon production in that year of 2014. So the organic carbon production started a little bit earlier and finished a little bit later that year, and it was increased. So the mixed layer depth was also a little bit shallower that year, and it just deepened to normal values below 80 meters of depth later that winter. And the halocline was a little bit shallower too. So during 2015, then we had the blob event, and again the El Nino feeding that blob for the second consecutive winter. And as we can see in here, again we have increased stratification during that winter, and we have higher temperatures in comparison to other years. What happened in that second consecutive winter stratification is that we didn't have a lot of organic carbon production. So organic carbon production, or MCP, started later that year, and it was in a very short period. If we take a look at the mixed layer depth in here, we see that during that winter, the mixed layer depth was much shallower than other winters. It was way above 80 meters of depth. And the halocline was shallow, but also this is the Brunt-Väisälä frequency in the background, and the darker the color, the more stable. We see that the halocline in the second year was very stable, which made us think that there was a double layer of clines preventing these inorganic nutrients to come up to the surface. So if we take that time series of net cleaning production and we integrate, we have total bulk of organic carbon production per year. So as we can see, until 2014, these are the peaks of organic carbon production for the previous years. And in 2014, this peak was a little bit elongated in that year, which means that really the organic carbon production was more spread throughout the year, but it was comparable to the other year. Then, after our second stratified winter, we see that this peak of organic carbon production was much reduced. If we compare the size of the peak with the previous years, we see that it was about third or fourth of the size of the other peaks. And also, there is a little and apparent delay in the organic carbon production in response to that shallowing of the mixed layer depth. So as we could see, this blue line here is the winter mixed layer depth anomaly. So the more negative, the more shallow the mixed layer depth in that winter. And the orange line is the summer net community production anomaly. So the more positive, more net community production happening that year in relation to our mean value for the data that we had. So in that first year, in that first stratified winter of 2013-14, we see very shallow negative mixed layer depth, and we see very positive net community production. And then it was only in the second stratified winter, when this mixed layer depth was already recovering, that we had this crash in the net community production, very reduced values that we find in this peak over here. So the combination of ocean atmospheric oscillations for 2 consecutive winters had a negative impact in organic carbon production, but only in the second year. Well, as we could see from that first figure that I showed the evolution of the warm events, in 2015, 2016, the El Nino was fully developed, but we didn't see a very warming ocean in the Northeast Pacific anymore. So the system actually recovered, and as we can see, the peaks are comparable to the previous year, the peaks of organic carbon production. But this blob plus El Nino teleconnections, they really impacted the ecosystem. Now we know that organic carbon was also impacted, but previous works already pointed to other consequences to the ecosystem. So just tracing a timeline of consequences of this warm blob and what we know that was going on. So in 2013, the blob started developing, common zooplankton population crashed, and fisheries spreads and shrimps declined that year in the region and a little bit north of Gulf of Alaska. So in that winter, the first stratified winter, we have a shoal of the mixed layer depth and a high stability that limited the winter mixing. And phytoplankton actually remained at the surface in that year. It was not diluted as it was always diluted in other winters. So in 2014, we had early net community production in that elongated peak of organic carbon production. And we think it's because the phytoplankton was already concentrated in the upper layer. Since it was not diluted in that stratified winter, the organic carbon production and the biomass, excess of biomass started earlier in that year. In that year, the blob and the El Nino they were already acting together, and we have again a second consecutive winter of shoal and stable of mixed layer depth. And we have an extension of net community production. So again, that year, the elongated peak. And as a consequence of the second stratified winter, our net community production or organic carbon production was near zero. For the first time, the region was a CO2 source. Zooplankton crashed in the California current. So remember that arc pattern that spread over the west coast of the United States only happened in that second year. And we saw consequences for the zooplankton and also harmful algae blooms. But in the winter 2015-2016, when the El Nino fully developed, we had a deepen of the mixed layer depth, and we had again nutrient ventilation. And then the system went back to normal conditions, if normal conditions exist. Zooplankton recovered, so that zooplankton, those species that kind of were in very low numbers, they recovered. But we saw declines in fisheries and shrimp catches even after the system recovered. So This study from Dilorenzo in 2016, they predicted that under a global warming forcing scenario, there will be a 16% chances of increases in frequency of these blob events happening in the North Pacific Ocean again. Not so much in that arc pattern trend, only 7%, but with the probability that these warm events become more frequent, what would be the impact of organic carbon production and sequestration in the ocean? And we can also ask if there is a third stratified winter or a fourth stratified winter, would the system be able to recover? For me, bioargo data combined with climatology assessment will continue to be a powerful tool to answer this question. So, for example, this study from which is 2016, they observed that while these warm events were happening in the Northeast Pacific Ocean, there was a connection with a cold blob event that was happening in the North Atlantic Ocean, and we don't know what happened with the organic carbon production during these events. So this is another interesting scenario to try to understand. So in summary, ocean atmospheric oscillation, the blob, the El Nino, we can call the arc pattern in between, they warmed Northeast Pacific Ocean for 2 consecutive winters and increased the upper ocean stratification. This vertical mixing restriction and reduced nutrient renewal had consequences to organic carbon production in the spring and summer months. So that first stratified winter had an early and increased net cone production, or that elongated peak of organic carbon production throughout the year. And then the second stratified winter was followed by that reduction in organic carbon production. The peak was a third or a fourth of the size of previous years. So the system could recover, fortunately, in 2016, after we didn't see this a third winter stratification. But these ocean atmospheric teleconnections brought unprecedented consequences to the environment, and now we know that it includes organic carbon production. And autonomous technology combined with insights into climate mechanisms, so these two fields combined together, I imagine it will continue to be powerful tools to address this question that could be emerging related to these studies or any next studies. And at this, thank you for your attention. If anyone has any questions.
Thank you, Mariana. That was a very nice presentation, and we've ended about on time here with the presentation. So we have about 10 minutes now for questions from the participants. We have about 17 people online. So please either raise your hand, use that feature, and I'll unmute you, or type your question in and I'll read it off for Mariana to answer. I have a question by Tony Lee. Tony, I'll unmute you. Here we go. Tony? Tony, can you hear me? For some reason, Tony's not coming through. Tony, if you want to type your question in, we'll come back to you. So, Allison.
Can you hear me?
Yes, I can.
You can. Okay. So my question is, and this is, I find this whole talk extremely interesting, and I know that the blob event was really something that stood out. Mm-hmm. But it occurs to me that one of the things that that we're seeing are these events which are really 2 to maybe possibly even 3-year events. And I was wondering if one could just use, say, the regular, not biogeochemical Argo, but the regular Argo to lengthen the time series, to get T and S and mixed layer depth and stability back in time, a couple of decades, and see what these cycles are, whether or not they produce a blob, but it may not be so important as whether or not these cycles have changed in character over the last couple of decades.
Yes. And when we did that, we actually did that for there is one work. I don't record the name of the author right now, but he found that the blob actually happened in the 50s.
Oh.
And so it already happened once. We have here, I don't think I have it here. Oh, here. So there is a blob event that's happening here. When we use the sea surface temperature and sea level pressure anomalies to try to understand what these patterns were, we could repeat what this author did for the 50s. So during the 50s, in here, there was a blob event. I think it was 57 or 58.
Okay.
So this already happened once.
Okay. So we have an additional question. Tony did write in a question. Are there biophysical models that reproduce the observed biophysical features associated with the event?
From my knowledge, I don't think so. No. There are several works on observational oceanography. Bones 2016 or 2015 was the first one who described the event in a physical way, but models, I don't think so. From what I read so far, I don't have the knowledge of that.
Okay. We have Shane Elapot. And Tony, if you have a follow-on comment, go ahead and type that in as well. I'm going to take Shane off of mute. There we go. Shane? For some reason, I'm not hearing you, Shane. I'll go ahead and ask his question. Would you say that the mixed layer depth is the main controlling parameter for these processes?
Okay. Yes. Yes, I would say. Because it controls the inorganic nutrients. So in the Northeast Pacific Ocean, the phytoplankton is not limited. The production of organic carbon in excess is not limited by nitrate. It's limited by iron. But the iron is also sourced by the deepening of the mixed layer depth. So yes, if we have a stratification, we prevent this renewal of inorganic nutrients and nitrate, iron, and other nutrients that come and can build up the biomass in the following spring and summer. So yes, I would say that the mixed layer depth is the main factor controlling.
So Shane points out that then these estimates of the mixed layer depth from historical Argo floats could be used as a proxy.
Yes.
Maybe.
Yes. Yes.
Yeah.
Yeah, but not for the organic carbon production itself, but yes, for a proxy of what events are happening and when. Yeah.
Great. Dennis Hansel had a question. Dennis, I'm going to take you off mute. Here you go.
Can you hear me?
Yes.
Yes.
Okay, great. Hi, Mari. So, Mari, looking back at your figure of summer NCP anomaly versus winter mixed layer depth anomaly.
Yes.
You know, there you go. The winter mixed layer in 2014 was somewhat negative, and then really deeply negative, shallow mixing in 2015. Yes. And so we just have a threshold issue going on here where you're moderate mixing, you're still reaching the right conditions with the nutrient and being entrained. But in 2000 you had such a shallowness that that's a consequence. That's below net community production. But in contrast to where I see you state that it's 2 warm years, I'm just wondering if your threshold that is the key.
Yes. So it was the first year. Yes, the first year was stratified, but not as deep. The mixed layer depth was still deep enough to renew nutrients. This is what I mean.
Right. So it may not be just. I'm just saying. Somewhere I read 2 warm years resulted in this outcome, say of a great NCP in 2015. But if we just isolate 2015, you have a very shallow mixed layer.
Yes. Yes.
So I'm just wondering if it's a threshold. You just, if you make some threshold of depth in the winter, you're going to have some good CP, and if you don't, it shuts it down.
Yes, it is a good question. And we can't answer because we don't have this combination to compare.
Okay. Thank you.
So Tony had an additional a comment that there's a 2018 paper by Yang et al. Based on analysis of observations that suggested annual net community production decreased during the warm event because of temperature-induced biological process. How is that related to your finding? So again, the question is the suggestion in this paper that annual net community production decreased during the warm event because of temperature-induced biological process.
It can be due to biological processes. We didn't measure the biology itself. We just know that it decreased. We don't know the reason. I also think that it was due to iron limitation, but again, we don't have iron measurements over there to explain why it decreased. We just know that it decreased.
Great. I had a question, Mariana, about your final comment about the need to sustain autonomous observing systems in the region. Can you elaborate on that a bit in terms of which observing systems have been critical to the work that you presented here?
Oh yes, the BGC float. This one. Okay, so these are SOCOM floats. They were equipped with nitrate sensors, but not only nitrate sensors, also oxygen, they have pH, they have chlorophyll for a few years, unfortunately not during this warm event. And they were deployed by Bernardi, and from 2009 and 2018. They were 6 floats, so here we see what year each float profiled the ocean. And these floats, they can profile down to 2,000 meters of depth. Every around 5 days, you have profiles of all of these biogeochemical variables and, of course, temperature and salinity. So they are Argo floats equipped with chemosensors. So, yes, these floats were crucial to understand because, I mean, nitrate is such a difficult parameter to go and measure, and we needed a high-resolution measurement to be able to do this work.
So the project that was supported to deploy these, is that continuing, or is there a renewal project that intends to continue deployments in the North Pacific?
I know that it's not a project itself, but I know that recently they deployed another float over there. Bari deployed another float there. Andrea Fassbender, she is funded by Export program, and that's how she deployed one more BGC float.
And then in addition, have you also been using the data from, say, the mortar rays in the Calcafi project, or other systems along the West Coast in the California Current?
No, I haven't. No.
Okay. All right. So, are there any other questions for Mariana? Okay, I don't see anyone raising their hand. I want to thank you, Mariana, and I see thanks from many of the people who asked questions in the box. We really appreciate the time you took to inform our panel, our committee, as well as the OCB participants who came online as well. So we will have a posting of your presentation by early next week, as I mentioned earlier. So anyone who didn't make the call, we can share that information that they can come in and see the presentation themselves. Okay, thanks everyone for participating. Our next webinar will be the first Thursday in April, and we'll be sending out information on that very soon.